Welcome to Scattering's blog. I'm the author G.V. Pawan Kumar. Recently, you have probably come across Oppenheimer, which has caught a lot of attention, mainly because of the Christopher Nolan's movie. And no doubt, Oppenheimer really deserves a lot of emphasis because he was a celebrated physicist and also did some wonderful kind of research related to black holes, in addition to spearheading the Manhattan Project. What is not emphasized that much is the fact that he did some outstanding research which was related to quantum physics, mainly from a molecular quantum physics viewpoint. So, what you see in this particular image is the image of his PhD advisor, Max Born. And of course, the image towards the right side is of Oppenheimer himself. So, Born and Oppenheimer played a very critical role in giving us a very important assumption, which is called as Born-Oppenheimer approximation. So, recently I did a thread on Twitter related to this particular Born-Oppenheimer approximation, and I thought I will also make a movie about this particular thread, so you can get some kind of an insight into what I have been writing about. So, roughly about 1920s or so, Oppenheimer and Born started working together. Born, of course, was in the then Nazi Germany, and he actually was doing some outstanding work. And Oppenheimer joined him to do research. And in 1927, they wrote a very important paper which was published in this Annal der Physics, which is a very celebrated journal where also Albert Einstein published his very important results. And this paper specifically played a very critical role in establishing one of the most important concepts in molecular quantum physics, and the approximation related to that, which is named after both Born and Oppenheimer. The important aspect about this particular paper, where I will also be linking a very important translation of the German paper into English, was mainly to establish a very important concept in quantum theory of molecules. So, what Born and Oppenheimer did was to actually come up with an approximation which essentially decouples the wave function of the nucleus from the electrons of a molecule. And the advantage is that it makes the calculation of the eigen energies, or what is also generally known as the quantum energy states, to be more feasible and accurate if they take this specific approach. And mind you, this is an era where people are still figuring out the foundations of quantum mechanics, and also the comparison with the experimental knowledge which is available from a variety of measurements, both on light and on matter, so to speak. So, the abstract of this paper highlights the concept very well. I have just highlighted a part of that particular abstract, and it clearly mentions that the specific ratio of the masses, in this particular case, it's the electron to the nucleus mass, which has to be actually calculated with the right fractional power associated with that. And their method ended up giving very accurate results. And you'll also see that this particular kind of calculation led to a comparison between a theoretical result and an experimental result in terms of the spectral lines. And I should emphasize here that the spectral lines played a very critical role in bringing the question of quantum aspect of matter into the foray, because spectral lines had discrete energy states, or discrete kind of lines in the electromagnetic spectrum, which was associated to the energy states of the quantum systems. So, therefore, this really motivated a lot of work, and it also kind of motivated many interesting experiments and theoretical explorations, and Born-Oppenheimer's paper really played a very critical role in that. What is interesting is that if you read the paper, especially the introduction of this paper, the first two paragraphs of the paper beautifully sets up the problem very nicely. They also mentioned that why one should take this particular fourth route, which is a very important change from just the square root of the ratio of the masses, and that plays a very critical role, because now you would be able to decouple the degrees of freedom of a nucleus of a molecule from the electrons which are present in the molecule, so that you would be able to now calculate the vibrational energy states, rotational energy states, and also the electronic transitions which are associated with the quantum nature of this particular system. Well, the story is not that much only because Max Born was a legend by himself. He played a very important role and established a very important insight into understanding the quantum mechanical nature of matter. Specifically, he gave the probabilistic interpretation of the wave function, where he associated the modulus square of the wave function to the probability density. This was a very important piece of work. He got the Nobel Prize for this work in 1954, where part of the citation mentions for his fundamental research in quantum mechanics, especially in his statistical interpretation of the wave function. Many thought that Born deserved Nobel Prize much earlier because most of the prizes were given in 1930s for great developments in quantum mechanics, and Born nevertheless got the prize, which he totally deserved, because without this clarification there was no physical insight of what it is to understand a quantum system, especially the interpretation of the wave function. Born was also a very important researcher during the pre and post war era period. He collaborated with many great scientists and also was a kind of a senior mentor to a variety of people, including Oppenheimer, Pauli, Heisenberg, Jordan, Fermi, Dirac, Wyckoff, Maria Oppenheimer, who also played a very critical role in two-photon interactions, etc., etc. Born also visited India, and he stayed at IISc on the invitation of C.V. Raman for about 6 months. There's a very beautiful story related to his visit and his interactions with Raman. He also did not have the exact matching of thoughts with Raman, because Raman actually was interested in the propagation of sound in a specific solid and the specific heat, and Born had a different interpretation of that, and there was some kind of intellectual argument between them, which is equally interesting if somebody is interested to follow. And I've anyway linked all these specific kind of citations in the thread, and I'll also be linking it as part of the show note down in the video. What is important is Born was deeply interested in optics. Okay, his interpretation of the wave function was mainly inspired by the definition of the intensity of the light, which is essentially the square of the electric field. So with Emil Wolf, Born wrote the magnum opus of optics, which is the Principles of Optics. This is one of the most celebrated optics textbooks which has been written. More than textbook, it is almost like an encyclopedic reference for optics, where it deals every aspect of optics and also lays foundations for further research in quantum optics and other interesting areas of research. And this particular picture, what you're seeing, is my personal copy of this particular famous book. I've also written about this book and also about both Born and Wolf about 5 years ago in a blog, which I'll be also linking as part of this particular thread. Born and Wolf collaborated on this book for a very long time, and this blog actually tells you and gives you some references of how they ended up writing this very famous book and how fascinating their research was, etc., etc. So finally, to kind of conclude, what I would want to emphasize is that, of course, Oppenheimer is a very celebrated physicist and has been a household name nowadays thanks to the movie. But a part of Oppenheimer and his making belongs to a great mind called Max Born. And Max Born is somebody whom we should be more aware of. And lest we not forget that Max Born did play a very critical role in shaping a lot of minds, including Oppenheimer. Thank you. Bye bye.